In Calculus 1, we learned the definition of the derivative of a function of x, and that is that dy dx, which we also call f prime of x, is equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. So if I started with a really simple function right now, let's say f of x equals x squared. We know how to find the derivative, but it turns out about half of all the formulas that we derived in Calc 1 came exactly from this definition here, including being able to differentiate things raised to powers. So let's apply this rule to here. If I want f prime of x, that will be the limit as delta x approaches 0 of x plus delta x quantity squared minus x squared over delta x. Now I need to expand and simplify. So that would be the limit as delta x approaches 0 of x squared plus 2x delta x plus the square of delta x minus x squared all over delta x. Now you notice at this point, the only two terms that do not have a delta x cancel beautifully. This usually happens in an algebraic solution of this nature. No trig terms, no exponentials. So I continue. And I will have 2x delta x plus the square of delta x on top over delta x. And now I can conveniently factor and cancel. And that would give me the limit as delta x approaches 0 of the quantity 2x plus delta x. At this point, I no longer have an indeterminate form, and when I evaluate the limit, I get 2x, which is what we already knew was the answer, but applying the definition of the derivative gets us to here. Now let's also review the differential notation we use in Calc 1. When we only have one independent variable, we use the differential operator d dx to indicate that we want to take a derivative. This is not a quantity, this is an operator. So I apply d dx to y, and I get dy dx. I apply d dx to f of x, and I get f prime of x. So the differential operator is the instruction to take the derivative of what follows. Now, if I wanted to take a second derivative, if I wanted to do d dx of d dx of y, we write that as d squared y over dx squared. Now, it might seem redundant that I have a 2 in both cases, but that will be evident when we do the multiple variable problem. That means the second derivative, that means both derivatives taken with respect to x. If I want to use the other notation, I just put a double prime. But if I continue this and I say I want to take several derivatives, like you did, let's say, with a Taylor polynomial in Calc 2, then if I wanted to do n derivatives, I would write it this way. Using the other notation, I would write it this way. Now the question always comes up about which notation do I use? Well, it's actually simple. If your function is defined as y equals, then you use dy dx notation, which is called differential notation. If your function is defined as f of x equals, then you use prime notation. Prime notation is reserved for functions only. There is no such thing as a variable prime. That actually would mean something quite different. Now what we want to do is establish the notation we're going to use with multiple independent variables. Now if I have a function of this form, I am telling you that x and y are now both independent variables, and z in this case is my dependent variable. So if I said take the derivative of z, that's ambiguous. I'd have to let you know, is it with respect to x or is it with respect to y? So now we'll have two differential operators, which we write this way. It's got a curvy d as opposed to a straight up and down d, and I also write it this way. These are my differential operators in this sense. These are what are called partial differential operators. The ones we did earlier with the capital straight up and down d's, those are called ordinary derivatives. So if I said I want the partial with respect to x of z, I write it as partial of z with respect to x. If I wanted the partial with respect to y of z, I write it partial of z with respect to y. The notation looks almost the same as it did in Calc 1, just the shape of my d is a little different. Now the question that you might ask is there an analogy to the prime notation? Well, I can't say f prime because that's ambiguous. It doesn't indicate which variable I'm using. So what we do in that case, if I'm using this notation, we write it like this: f with a subscript of x. In this case, f with a subscript of y. This is our analogy to prime notation. I like this notation because it's easy and it's not ambiguous in any way. Now, if we wanted to take a higher derivative, I could take the derivative of this quantity with respect to x or with respect to y, and then the same thing here. So if I said I want the partial with respect to x of dz dx, then we would write that this way. If I said I want to take the partial with respect to x of dz dy, I would write it this way. Notice that 2 still indicates that it's a second derivative. This says I did x twice, this says I did x and I did y. And then finally, if I said the partial with respect to y of dz dx, now, all 3 of these are called second order partial derivatives because they're second derivatives. This one and this one are called cross partials. And it turns out it doesn't matter what order, as we will see, you will get the same answer if I take one derivative with respect to each variable, which is actually quite convenient. Now let's establish the formal rules for taking the derivatives in higher dimensions. Now the formal definition, given a function of 2 independent variables, the partial of z with respect to x looks very much like our definition of the derivative for Calc 1. As delta x goes to 0, I have an f of x plus delta x. As delta y goes to 0, I have an f of y plus delta y. But notice only one variable is affected at a time. This is called a partial derivative for a reason. I'm only taking derivative of part of it at a time. So what we're going to do in this case here is expand it in much the same way we did in Calc 1, and we're going to see the benefits and the shortcuts that are involved. So let's consider a function, I'll keep it really simple. Z is 2 times x squared times y cubed. So if I said what is the partial of z with respect to x, then that would be the limit as delta x approaches 0 of, now I want to replace the x with x plus delta x. So that would be 2 x plus delta x quantity squared y cubed minus 2x squared y cubed all over delta x. And similarly, the partial of z with respect to y would be the limit as delta y goes to 0. Now what I'm going to do is replace the y term. So I'll have 2x squared y plus delta y quantity cubed minus 2x squared y cubed all over delta y. Now we'll go ahead and expand these and see what we get. But what we're going to find is there are some tremendous shortcuts that we're going to be able to take. To speed things up a bit, I've gone ahead and expanded the numerator, and it turns out the only term that won't have a delta x in it is this one, and it canceled, leaving us this quantity. When I factor and cancel the delta x, I'll have this quantity, and now I can take the limit, leaving me this. So the end result is the partial with respect to x of this quantity is this. Pay particular attention here. I said take the derivative with respect to x. If I differentiated 2x squared, I simply get 4x. And our answer looks like that's all I did. Well, it turns out that's all I have to do, as we're going to show in a moment with the y term. Now, when we take the derivative with respect to y, we have this quantity here. And once again, I went ahead and expanded the numerator, and the only terms without a delta y will cancel, leaving us this. When I factor and cancel out a delta y, I get to here. There's only one term left without a delta y. So when I take the limit, I get this quantity here. So our end result is the partial with respect to y of this quantity is this. And once again, we notice if I had simply taken the derivative of the y term, 3y squared, I'd get this quantity. So now the question remains, is taking a partial derivative really this simple? It turns out the answer is yes. So we're going to do a couple more examples just to show you how easy you can power through this, and then I've put a very large number of examples on the posted notes. Now let's do a simple example. I have a function here of two variables, and I want to take the derivative with respect to x. The simplest way to see this is every variable that is not x, think of as a constant. So right now that xy is basically x times a constant. X squared y is x squared times a constant, and y cubed is simply a constant. So when I take the partial with respect to x, I'm going to get the cosine of xy times the derivative of xy. But the derivative of xy with respect to x would simply be y, because that would be the chain rule factor. The derivative of this term with respect to x, I'll have 6x times y, because y is treated as a constant. But because this only has y's in it, the derivative of the constant is 0. So I'm done. That's the entire answer. Now let's do something similar with respect to y. Now I have y squared times a function of x, so now the function of x is treated as a constant. So the derivative of the y term would be 2y, and then that. This would be 0 because there's no y in this term at all. And finally, the derivative of 3y would just be 3. Now you want to get lots of practice at this because taking derivatives in higher dimensions is going to be the order of things for a little while. Turns out we can actually have more than two independent variables and all the rules will be exactly the same.